AVL-AST Simulation Technologies has developed a suite of software which makes the vision of the virtual engine a reality. With this set of highly sophisticated yet easy-to-use software products, all the calculation and simulation tasks involved in developing an engine can be readily performed. The engine cycle simulation, usually the first task, is done with AVL-AST. This new thermodynamic software provides extended calculation capabilities and easy-to-use graphical pre- and post-processing. Shown here is the pressure distribution in the intake and exhaust pipes of a 4-cylinder gasoline engine. Animations like this are routinely produced on screen with BOOST's powerful post-processing module, which gives the user a clear and quick understanding of the engine's characteristics and all calculated results. Optimization of the mixture formation and combustion is one of the most challenging tasks in engine development. FIRE, a general-purpose computational fluid dynamics package with outstanding performance and accuracy, has matured into a valuable engineering tool in this particular area. Other typical FIRE applications include, for example, internal and external car aerodynamics, cooling flows, and catalytic inverters. Shown here is the flame front propagation in a 4-valve gasoline engine, which was simulated by use of a transported PDF combustion model. The combination of sophisticated physical models and accurate numerical techniques delivers valuable results. Shown here is the spray propagation together with the temperature field in a high-speed direct injection engine. Other examples of FIRE applications are the injection, mixture formation, and combustion processes in diesel engines. The quality of the calculated results depends on how well they compare with experimental measurements. AVL has laboratories equipped with optically accessible engines which address this topic by use of state-of-the-art techniques including laser Doppler velocimetry, laser-induced fluorescence, and tomographic combustion analysis. Regarding the valve train and timing drive dynamics, AVL has developed TICON, which can not only simulate a single valve, but also the whole timing drive including camshaft, belt, or chain drive. Shown here on the right-hand side are the torsional vibrations of the camshaft and its influence on valve lift. The nominal motion of the camshaft and valve is shown in red, whilst their actual motion is shown exaggerated in gray. For reference, a complete valve is shown on the left-hand side. With TICON, the dynamic behavior of all valve train parts, like shafts, belt, or chain drives, can be evaluated and optimized. TICON can also be used for the calculation of gear transmission dynamics. Another point of interest in the engine is the piston and piston ring group, simulated with the software package GLIDE for piston dynamics. The results of this simulation are used for acoustics calculations through analysis of piston slap or for the estimation of lubricating oil consumption. Shown here are the deformed cylinder liner and piston shape caused by temperature and the piston side force and tilting motion. Based on these results, further calculation steps in GLIDE simulate the piston ring dynamics and calculate blow-by and lubricating oil consumption. Linked with finite element calculations for cylinder liner deformation, the optimization of lubricating oil consumption can be performed. For crankshaft and bearing design, AVL has a set of tools, for example the package BRICS for torsional vibrations and basic bearing design. With AVL's Excite module for elastohydrodynamic bearing calculations, the nonlinear influence of the oil film on structural deformation can be simulated. Shown here is the conrod big end bearing, and you can see the deformation of the bearing and conrod caused by the oil film pressure. For the calculation, Excite uses the stiffness matrix of a finite element model of either the conrod big end structure, as shown here, or of a main bearing. Now you see the pressure of the oil film represented by the height of the pressure peaks. Excite can take into account the influences of oil supply ducts and grooves, of split lines of the bearing shells, and also of pin misalignment, giving the engineer all the data he or she needs for the design of highly loaded bearings. The main application of Excite is, however, the nonlinear forced vibration calculation shown here for a 4-cylinder gasoline engine. You are seeing a visualization of the forced vibrations of this engine, including the gearbox, intake and exhaust systems, and auxiliaries, as well as the engine mountings. Taking into account the realistic excitation forces of the valve train, calculated with Tycon, and those of the piston impact, calculated with Glide, absolute noise levels are obtained. The heart of the simulation is the movement of the rotating crankshaft and the excitation forces of the nonlinear oil film, shown in the next sequence, where the influence of the torsional vibrations is also clearly visible. The evaluation of crankshaft dynamics is another application of Excite. To summarize, we can confirm that the vision of the virtual engine has become reality with AVL's advanced software tools.